Welcome back, Focus Learners. I'm so thrilled you're tuning in today because, well, we are charting a really fascinating course. In this explainer, we're going to take a journey starting from the absolute foundational basics of chemistry, and we're going to carry that all the way up to international competitive mastery. If you've ever wondered exactly how the brightest young scientific minds organize both the universe and themselves to compete on a global stage, you are absolutely in the right place. So, let's jump right in. The International Junior Science Olympiad, or IJSO for short, is honestly not just a test. It's really more of a grand quest. It is the ultimate event where India's brightest young scientific minds compete against their global counterparts. But here's the secret. Conquering this massive worldwide challenge, it doesn't actually start with crazy, complex university-level equations. It starts right here, with mastering the absolute fundamental concepts of chemistry. Grasping what makes up our physical universe is quite literally the key to unlocking this global arena. Okay, here's our agenda for today's explainer. 1. The Olympiad Roadmap. 2. Matter versus non-matter. 3. Physical states of matter. 4. Chemical classification. And 5. Inside the atom. Section 1. The Olympiad Roadmap. Charting your path to the IJSO. Now, you don't just walk straight into the global arena, right? It is a steep climb. First up, you've got the NCERT. This is the critical first qualifier, and it tests the foundational Class 9 and 10 syllabus. Once you pass that, you face the IJSO, an advanced test that really turns up the heat on theoretical and practical challenges. Then comes the OSCC, which is a super intensive selection camp, and that's followed closely by pre-departure training for that final polish. Only after conquering every single one of those stages do you reach Step 5, the International Junior Science Olympiad. And remember, each rigorous stage builds entirely on the foundational knowledge of the previous one.
But let's be real for a second here. Conquering this roadmap is definitely not a solo mission. It requires a really strong mutual commitment to success, basically a handshake agreement between the instructor and the student. As an educator, the solemn pledge is always to explain every single concept from the very basics to cover the entire syllabus and honestly to work even harder than the student to ensure their success. But as you might guess, a pledge like that requires something equally intense in return.
And that brings us to the winning protocol. If you want to reach that global arena, there are strict rules of engagement. You must attend class regularly, no skipping, you've got to revise your class notes daily. And here's a massive one. Finish the same day's work on the same day. Do not let it pile up. You need to attempt every test honestly, and absolutely positively stay away from distractions. Basically, if the teacher is working harder than you, your end of the bargain is to clear the path of any distractions so you can actually absorb the knowledge.
Section 2. Matter versus non-matter. Defining the physical universe.
So let's shift gears from that motivational macro view into the scientific macro view. What exactly is the universe made of? Well, we've got to draw a really stark line right here. On one side, we have matter. For something to be considered matter, it absolutely must possess mass and occupy a definite volume, meaning it literally takes up space. It's composed of discrete physical particles like atoms or molecules. Think of a pen, a cloud of smoke, or the air you're breathing right now. Conversely, on the other side, we have non-matter. These are forms of energy or abstract concepts. They do not possess mass, and they definitely do not occupy physical space. Things like heat radiation, sadness, sound, or electricity.
Okay, let's test this out with a real-time challenge straight from an advanced physical chemistry lab. Imagine you're standing there, observing this incredibly intense green light being emitted from a helium-neon laser tube. Is this light classified as matter or non-matter? Think back to our definitions for a second. Does that beam of light have mass? Does it take up physical space in the room?
If you guessed not matter, you nailed it. But why? Well, because laser light actually consists of photons, and photons do not occupy physical space, nor do they possess any rest mass. Contrast that with actual matter that you might find in that very same lab. For instance, a beam of alpha particles, which have actual helium nuclei in mass, or maybe dense smoke from a combustion reaction. That smoke is actually just solid carbon particulates physically suspended in a gas, so it takes up space and has mass.
Section 3. Physical states of matter. From extreme cold to extreme heat. Now that we know what matter is, how does it physically manifest? Well, it depends on temperature and the attractive forces between its particles. When we sequence the states of matter by their energy level, a really cool picture emerges. Right in the middle, we have the three we're all super familiar with, solids, where that intermolecular attractive force is at its absolute maximum, packing particles tightly together. Add a little heat and you get liquids with slightly lesser attractive force. Add even more heat and you get gases,
where there's the least attractive force and particles are just bouncing everywhere. But look at the outer edges of this spectrum. On the extreme cold end, we find the Bose-Einstein condensate. And on the extreme hot end, we have plasma, a super hot ionized gas. And actually, you've seen plasma in everyday life. It's exactly what makes up lightning, or even the glowing gas inside a neon tube.
Section 4. Chemical classification of matter. Pure substances versus mixtures.
So we just looked at physical states. Let's zoom in a bit further and see how matter is categorized chemically based on its purity. There's this fundamental divide in chemistry, and the ultimate question you have to ask yourself is this: can this substance be separated using physical methods? If it cannot be separated by physical methods, like filtering or boiling, then you're looking at a pure substance. That includes elements and compounds. But if it can be separated by physical methods, you're dealing with a mixture, which we classify as either homogeneous or heterogeneous. Let's break those down really quick.
First up, we've got the element. This is a pure substance made up of just one type of atom. It is the absolute simplest chemical form, meaning it cannot be broken down into simpler substances by chemical means. Think helium gas, nitrogen, oxygen. Now, when atoms of the same element bond together, they form molecules. And the total number of atoms in that specific molecule, that's what we call its atomicity. So, an oxygen gas molecule, O2, has an atomicity of 2. But here is a truly wild fact. Even visually complex solid structures like a diamond, graphite, or a Buckminster fullerene, those really cool soccer ball-shaped molecules, they are actually just pure elements. They're made entirely of carbon atoms.
Next, we have the compound. This is a pure substance formed when two or more different elements combine chemically in a perfectly fixed ratio. Think of water, H2O. It's always going to be 2 hydrogens to 1 oxygen, which gives it an atomicity of 3. Or carbon dioxide, CO2, also an atomicity of 3. But what's genuinely mind-blowing about compounds is how their properties can transform completely from their base elements. Look at water again. Hydrogen on its own is highly flammable. Oxygen actively supports combustion. But when you combine them chemically into H2O, boom, you get a fire extinguisher. The resulting compound has completely different properties from the elements that made it.
Moving over to the mixture side of things, we start with homogeneous mixtures. This is a physical combination where the composition is completely uniform throughout. Importantly here, no chemical reaction has actually occurred, which means the components totally retain their original properties. Pure air is a fantastic example of this. It's just a uniform mix of nitrogen, oxygen, and some other gases. Or take a metal alloy like brass. It looks like one solid single metal, but it's actually just a really uniform physical mixture of copper and zinc.
Now contrast that with a heterogeneous mixture. This is a physical combination that has a non-uniform composition throughout. Usually, it's pretty visually obvious that you're looking at multiple different things mixed together. Think about sand just sitting at the bottom of a glass of water, or oil floating on top of vinegar. Heck, even milk, if you look at it under a microscope, is actually a non-uniform dispersion of fat globules floating in liquid. And because they are mixtures, you can easily separate these out using physical methods.
Section 5. Inside the atom. Zooming into the subatomic level.
Okay, we're taking our final zoom inward today. We're leaving the visible macro world entirely behind to look at the very building block of all those pure substances we were just talking about, the atom. It is literally the foundational building block of matter. For a little historical context, John Dalton, way back in 1808, proposed that the atom was completely indivisible. Actually, the word itself comes from the Greek atomio, which means uncuttable. But as science advanced, that uncuttable theory had to be tossed out. Why? Because we discovered that the atom isn't just a solid, boring sphere. It is a bustling miniature solar system made up of even smaller subatomic particles.
Let's quickly break down this subatomic anatomy, because it's actually a beautifully simple spatial arrangement. Right in the very center, you have the heavy stuff, the nucleons. These are particles living inside the incredibly dense nucleus. They consist of protons, which carry a positive charge, and neutrons, which are perfectly neutral, no charge at all. And then, flying around outside this nucleus in distinct paths, you have the electrons. These are incredibly light, negatively charged particles. And it's this exact delicate balance of positive protons and negative electrons that gives matter all of its chemical properties and makes our entire physical universe work.
And that brings us to the end of today's deep dive. We have traveled all the way from the macro goals of conquering the International Junior Science Olympiad right down to the micro-orbit of a single electron. You now know the strict protocols for studying, the stark difference between matter and energy, how matter is classified by atomaticity and composition, and the core anatomy of the atom itself. Your foundation is solidly set, so the only question left for you as a focused learner is this: what complex chemical reaction are you going to master next? Keep studying, stick to the protocol, and I'll see you in the next explainer.